Solve the equation by completing the square. Here's our equation. The first thing you do is divide by the leading coefficient first. The coefficient of the x squared term. But that's 1 on this particular problem. So dividing 3 by 1 doesn't change anything. But you would always do that first. So then we have to get rid of this term here in the procedure by adding 3 to both sides. So adding 3 over here and adding 3 there cancels it off of here and moves it over to the right. Then the procedure is whatever this term is here, we take half of it and square the whole thing. So half of it is in here, and then we square the whole thing and we add that to both sides, the exact same number. Then we clean up the algebra a little bit. 1/2 of -4 is -2, and that's being squared. 1/2 of -4 is -2, and that's being squared. Then we square it out. We get the 4, and we get the 4 over here. Now, the reason why we did all that was to be able to write the left-hand side as a squared out binomial. In other words, this is a perfect square trinomial. Perfect square trinomial. That's what that is. So it comes from a squared out binomial, and you can see that square root of 4 is 2, and there's got to be a minus. There has to be a minus sign there, so you have to go x minus 2 squared, and you can square it out quick as a check. X squared multiplied together -2x, -2x doubled is -4x, -2 squared is 4. Then on the right side, 3 plus 4 is 7. Now you're going to take the square root of both sides. Or, in other words, what do you have to square to get x minus 2 squared? X minus 2. And what do you have to square to get 7? Square root of 7. But it's plus or minus. Why is that? If you have the plus and you square that, the square of the square root of 7 is back to 7. If you have the minus and you square that, you also get a plus 7. So both of those work, plus or minus. Then you add 2 over to both sides. Add 2 plus 2, and end up with x equals 2 plus or minus the square root of 7. So you break that up into an or. X equals 2 plus square root of 7, or x equals 2 minus square root of 7. And those are the two solutions to the original equation. Now it's interesting to note that the fact that these solutions came out irrational, in other words, not fractions or integers, but square roots, irrational numbers, means that the original quadratic polynomial on the left side of the equation does not factor with integer coefficients. And just to show that, here's the original quadratic. You set up the template x. 3 is prime, so only 1 and 3 will work. You try the signs plus, minus, because it has to be a negative, so it has to be opposite signs. You try those, but that adds up to -2, not -4, so that one doesn't work. Then you try it with a minus sign here and a plus sign there, but that adds up to plus 2x, and that doesn't work either, so all your possibilities don't work. So this will never factor the way we're used to, because the answers are irrational. And now we're going to check this with a calculator check. Make sure we really do get those answers. Here's the original. We put it in the calculator. We graph it. We're looking for this root and this root, so we do a second calc 0 to find this one, And there it is, negative 0.64, etc. And then we do second calc 0 again to find this root, and it's 4.645, etc. And when you write out the decimal versions of 2 plus square root of 7, you get this one. And 2 minus square root of 7 is this one. I forget to put the negative there. That is a negative number. And so it checks out. This checks out with this one, and this checks out with this one. Alright, now go on to a different example. So this one we have this here, and divide by the leading coefficient in this method, divide by 2, that's 2, throughout, and you get a little fraction here, but that's okay. So here's your resulting. Now this function here does not have, it's not the same function as the original because it's off by a factor of 2, but it does cross the x-axis at the same place. It crosses the x-axis at the same place, and therefore it has the same roots. So it still has the same solutions as the original did. So now we add 6 to both sides. It crosses off to the left, adds on to the right, and we get this. Then we take half of this term, the x term, and square it. So half of it and square, and we add that to both sides. Half of it squared. Then we clean up the algebra. Negative 5/4 is in there, being squared. Negative 5/4 is in there, being squared. Now, what we're going to do here is go ahead and not square this out. We can, but it doesn't matter, because we're going to know this is a perfect square trinomial, and the binomial that squares to get that is x minus, because it's a minus, and 5/4, so that if you squared the 5/4, you'd get 5/4 squared, and if you multiply these together and double it, you get 5/2, so it works. Then on this side, I am going to square it out, 25/16. Then I have to add those together over here. That's 96/16 plus 25/16, converting into sixteenths, and that adds up to 121/16, and this just copy down each time. Then here I take the square root of both sides. X minus 5/4 would equal plus or minus the square root for the same reason as it did in the previous problem. So that's plus or minus, and this comes out nice. 11/4 is the square root of 121/16. Then you add 5/4 to both sides. It comes over to the right side as positive. So then you break it up at that point. X equals this, or X equals that. And then you add these together, and you get 16/4, which is 4. And over here it's 5 minus 11 is negative 6/4, which is negative 3/2, reducing. So your two roots are negative 3/2 and 4. The fact that these solutions are both rational means the original quadratic polynomial on the left side factors. So let's verify that. So here's the original, and if you factor it like this, you'll see it works. Negative 8x plus 3x, negative 5x. 3 minus 4 is negative 12. And also you can see that the roots are in there. Negative 3/2 plugged in here makes this 0. And 4 plugged in here makes this one 0. So it's all matching up. The roots give you the factorization gives you the roots. So when you're completing a square, if you're doing it on an original polynomial that would have factored, then you're going to get rational roots. If you're doing it on a function like this, such as the original, this one, and you get irrational roots like these two, then that means the original polynomial did not factor.